Hi everyone, welcome to Mostly Math. Today we will be looking at the following identity. We're going to be deriving the fact that zeta prime of 0 is negative 1/2 log of 2 pi, where zeta is of course the Riemann Zeta-Function. Also note, I cannot draw the letter zeta. It's supposed to look something like this, but I can only draw it if I go very slowly, so I'm not going to do that. So if you see a weird squiggle thing, it's probably the zeta. Okay, where it's defined as follows. Zeta of s is the sum of 1 over n to the s from n equals 1 to infinity. We're going to be looking at the derivative of the zeta function, evaluated at 0. But first, let me note that we already know that zeta of 0 is the following sum, which is 1 plus 1 plus 1 plus etc. is equal to minus 1/2. This is a very famous result. It can be derived the same way that you can derive zeta of 2. It's the same formula. Zeta of 2 is just adding up all the squares. 1 plus a fourth plus 1, 3 squared is 9, plus 4 squared is 16, plus etc. is pi squared over 6. Excuse me. It's actually a formula that relates all the even numbers, all the even arguments of the zeta function in terms of the Bernoulli numbers, which is a very famous elementary property which has been done thousands of times. I might do it later, but that's not the point of what I'm doing today. I was having trouble finding a reference for this identity here. I looked through several papers which all led me to other papers which only cited the result and didn't quote it until I eventually found a book from the 80s about the properties of the zeta function, which finally had the proof which I'm going to show you today. First, let's talk about the derivative of the zeta function in general. So, we're going to need following things. We're going to need following facts. We're going to need that the derivative of an exponential is simply the exponential times log of the base. Gonna need that. Now we can look at the derivative. Zeta prime of s is just going to be, so s is the variable here. We have n to the minus s, and if we take the derivative with respect to s, it's just going to be n to the minus s times the derivative of this, which puts a minus sign. Then we have log of the base here. That's what we're going to do here. Simply the sum from n goes from 1 to infinity. There's a minus sign. Log of n over n to the s. So if we're looking at zeta prime of 0, we're actually looking at minus the sum of 0 here, which becomes 1, log of n, which is minus log 1, which is 0 of course, plus log 2, plus log 3, plus etc. We're going to be showing in this video that it's equal to the following constant, which can also be written in the following way. Log 1 over square root of 2 pi. So it's cool that 2 pi comes in. It's not really surprising that there's a log in the final answer because we're summing up logs. So that's good. We'll be showing that today. Okay. I will, of course, be leaving a link in the description for the book that I found this in, so you can follow the argument for yourself. It's quite interesting. Okay, we're good to go. The next part, I do need my notes because it's a pretty involved formula. There's going to be lots of approximations, Taylor series. It gets pretty intense. Okay, starts off from the functional equation for the zeta function. which tells us that zeta of s satisfies the following relation: 2 to the s, pi to the s minus 1, sine pi s over 2, gamma of 1 minus s, zeta of 1 minus s. So now we have here the Riemann zeta function, which we've talked about in previous, this is a zeta function. This is the gamma function. It generalizes the factorial function. I've talked about it before. We are now going to obtain a similar relation by plugging in. If I let s go to 1 minus s, I'm going to have zeta of 1 minus s is equal to 2 to the 1 minus s pi. Okay, 1 minus s minus 1 is minus s. This becomes cosine. I'll show you why in a moment. This becomes gamma of s, and this becomes zeta of s. So this is pretty easy to see. And we're going to use the identity sine of pi over 2 minus x is equal to cosine x. So I had up there sine of pi over 2, 1 minus s. This is simply sine pi over 2 minus pi s over 2, using this identity, just cosine pi s over 2. That's the first step. I think we can all buy that. It's pretty straightforward. And now that we have this, we basically want to get the derivative, but the derivative is a bunch of terms that we would have to apply the product rule with. We don't like a bunch of products. We would rather have a sum. So we can take the logarithmic derivative and go from there. So we're also going to note here logarithmic derivative. The derivative of the log of a function of x is just f prime of x over x, f of x, sorry. Since the derivative of a log is 1 over the function, and then you take the derivative by the chain rule. So we're going to take the derivative and then the log from there. Show you where we're going. Okay. d by dx log of everything. d by ds, sorry. It is d by ds log zeta of 1 minus s is equal to, going to take the log first and then do the derivative. Okay, first let me make sure I have the functional equation correctly. No, I do not quite have it correct. You can actually write this in a simpler form. You can take out one of the 2's and write it in the following way. This is the form that we're going to use. I mean, what I wrote there is correct. It's just not as cool as this. Okay, we need this. This is going to help us. Okay, so we have the log of 2, which is going to go to 0 as we take the derivative. When we take the log of this, we get a minus s coming down, then log of 2 pi. This doesn't really simplify it this time. Log of cosine pi s over 2. And the other ones don't simplify yet either. But they will in a moment, don't worry. Okay, first thing we're going to note is that this is actually a special name if we take this through. I'm going to look at the Diagamma function of x, defined as the logarithmic derivative of the gamma function. So that should be pretty easy to deal with. This will be easy to deal with in a second. So let's just go ahead and do that one. Make sure I did this right. Yeah, it looks good. So d by ds of log cosine. I'm gonna need another step. So okay, d by ds log of cosine pi s over 2 is just the derivative of cosine pi s over 2 over cosine pi s over 2. Well, we can certainly do that. Doesn't seem very bad. We get the derivative of cosine is minus sine. with the constants coming out over, this is the same. So it becomes minus pi over 2 tangent of pi s over 2. So that's good. Okay, and we're also going to take care of a small issue here. So we can actually note that d by d 1 minus s is the same thing as minus d by ds. So we can write this as minus zeta prime of 1 minus s over zeta of 1 minus s is equal to whatever crap we get on the other side. Okay, so this term is easy. Did this term. This term is just the Diagamma function. So let's write down what we have so far. This is simply minus 2 pi minus pi over 2 tangent pi s over 2 plus the Diagamma function of s plus the tricky term here, which we're going to look at in a moment. Okay, so we have d by ds log zeta of s. Unfortunately, the Zeta function is not as well studied or understood, so there's no cool formula for me to just apply. Yeah, got it right so far. It's looking good. Yep, looks good so far. Actually, I'm going to write this in the other form. Zeta prime of s over zeta of s to be analogous with the left-hand side. Yep, looks good so far. So now we want to evaluate this at s equals 1. We want to put s equals 1 everywhere so we get zeta prime of 0 over zeta of 0, which we know from the intro, on the other side. But we can't just go ahead and do that. We have to actually Taylor expand. Otherwise, this term will go to 0, won't tell us any information, and we won't get what we want. We won't get the logarithms. Let's go ahead and Taylor expand it at s equals 0, s equals 1. We need some Taylor series. So, you can show that the following is true. You can show that at x equals pi over 2, tangent of x is approximately minus 1 over x minus pi over 2 plus higher order terms, which are proportional to x minus pi over 2. And I am going to prove this now by showing that it has a residue of minus 1. Let's do that. Residue at x equals pi over 2 of sine of x over cosine of x is equal to limit x goes to pi over 2 of x minus pi over 2 sine x over cosine x, which is, using L'Hopital's rule, the fundamental trick to use in this situation. Derivative of this first is 1 sine x plus derivative of the other function, which is just cosine x over cosine x. No, have to take the derivative of that too, right? Okay, that's minus sine x. Now we have to evaluate it at x equals pi over 2. So this becomes 1, this goes away, this becomes minus 1, tells you that it's minus 1. Okay, and from that, we can substitute variables in pretty simply to show that pi over 2 tangent pi s over 2 at s equals 1 is 1 over 1 minus s plus higher order terms of 1 minus s. I trust that you could make the substitutions and do that if you want to. I believe in you guys. You can do it. You can do it. Making sure I got it right, since you're going to take my word for it. All right, we need the other one now. So we have all the terms except this bad boy here. We have to evaluate this at 0 as well. Or 1 rather. Yeah, to evaluate it at 1. At 1, not at 0. Okay, so let's go ahead and do that. This one I'm just going to quote because it is extremely difficult. So we also know that the following is true. Zeta prime of 1 minus s over zeta of 1 minus s is approximately at the point x equals 1. 1 over 1 minus s plus the Euler-Mascheroni constant plus higher ordered terms of order 1 minus s. I need these to be equal and opposite, so perhaps I made a mistake somewhere. No, I didn't. I didn't because there's a minus sign attached to this bad boy here. There's a minus sign, so it's good. Okay, and there's one more thing we need to discuss. We also need to discuss diagamma, which I'll just put here, I suppose. So, we know the following formula for diagamma of s plus 1. It's going to be minus the Euler-Mascheroni constant plus the sum as n goes from 1 to infinity of s over n plus s. So this tells us that diagamma of 1, which is the value we need, is simply minus gamma. And now we're ready to put it all together, aren't we? Finally. Oh, how did I derive this, you might ask? I didn't derive it. I can tell you that the first term is there, and as for the second term, it's more difficult. But basically, if you want to derive what I did, first you can use the following expansion for the zeta function. You use the fact that zeta of s is approximately at s equals 1. Minus 1 over 1 minus s plus the Euler-Mascheroni constant plus some constant times 1 minus s plus higher order terms of 1 minus s squared. Then you take the derivative, which is, you just take the derivative of this and the constant goes away, and that's a constant as well. And you divide them using polynomial long division, and you can obtain this formula here. But as for how this formula is derived, I really don't know, but it's not the point of this video. I can't derive everything. I'm sorry. I just can't do it. It's going to take too long. All right. Now we can put it all together. Pretty sure. So now we evaluate s goes to 0. 1, sorry. S goes to 1. So minus zeta of 0 prime, which is what we want, divided by zeta of 0, which we know is now equal to minus 2 pi. Does that stay there? I guess it does stay there. It needs to be minus log 2 pi. Sorry, I made a small mistake earlier. Thought that didn't look right. So the mistake was I just got rid of the log, but really this just takes the derivative and the log stays there. Where was I? Let's put it together. Okay. Minus log of 2 pi minus 1 over 1 minus s plus our diagamma value plus this thing that we have up here plus higher order terms, which these bad boys cancel. These bad boys cancel. So it's minus log of 2 pi. And now, in whatever space I have left, So we have zeta prime of 0 is equal to minus zeta of 0 log of 2 pi. And we learned that this was minus a half earlier. I shouldn't have a minus sign here. Ah, yes, because there's a minus here. This minus does go away. Minus 1/2 log of 2 pi. Certainly sorry about that. This is tricky stuff, as you can see. It's tricky to give the lecture for. It's tricky to derive on your own. There's a lot of moving parts here. I'll refer you to the book if you'd like a less detailed explanation. And there will be an application of this in a future video. Don't worry, I'm going to use this for something. Going to basically multiply all the integers together and show that this value is extremely important in deriving that. Sorry for the mistakes, but it's very tricky. If you can do better, please let me know in the comments, and if you have any more suggestions, I'll see you next time. Have a great day.